Section 15.2 is line integrals. And to sort of just prompt our discussion of what we're doing here, one of the things that we did, you did at one point, you took Calc 2, is and this is in section 15.6 of this particular book, you showed that for a thin rod with a variable mass density extending from A to B, the mass of the rod was given by the formula integral from A to B, and the mass density was rho of x dx, that we could find the mass of the rod by using this formula. However, to find the mass of a three-dimensional object, such as a helical spring, and there's a picture in your book, so you're imagining a spring, okay, and we must extend this idea to 3 dimensions. So that's where we're starting, is we're going to take something we've done in Calc 2 and extend it to 3 dimensions, which is what we've done a lot of in Calc 3 and Calc 4, is you just do an extension of what we've done before, right? So to take this idea, we're going to take definition 2.1, and we're going to write out some of those details. So definition 2.1 is the definition of a line integral. Specifically, it's a line integral with respect to arc length, and we're going to do another line integral later. So the line integral and I'm going to do it in 3 dimensions, and then I'll sort of mark out the pieces so you can see what it looks like in 2 dimensions, so we don't have to write it twice. The line integral of f of x, y, z. Oh no, that's not one of the ones I'm going to do this for. This is for 3 dimensions. There's a 2-dimensional thing later we're going to do. With respect to arc length, along the oriented curve, C, in 3-dimensional space, and we'll abbreviate 3D space. Written the integral along the curve of f of x, y, z, and it's with respect to with respect to arc length, which we use the letter S by, is defined by the following. So here's our integral that we just wrote above. This equals the limit as the size of the partition goes to 0 of the summation from I equal 1 to n f of xi, yi, zi, delta s sub I. And we've had these kind of things before where we've then had to put this disclaimer, if you will, at the end. Provided the limit exists, that's obviously important or this won't make sense. And then the second disclaimer is, and is the same for all choices of evaluation points. And we sort of get around worrying about the all choices of evaluation points because our partition is going to 0. So it ends up being sort of an unnecessary thing to worry about as we continue through the process. That's great, but we've also got the ability to use integrals in order to take those limits, and that's a theorem that we're going to do next. So this is actually going to show what it looks like when we actually employ this theorem. okay, what this is actually going to do. Am I okay to switch the slide? Okay. All right, so theorem 2.1, it's called the evaluation theorem. And it says the following, and this is, I think this is the one. Yeah, I'm going to write this in terms of the three-dimensional one, and then I'm going to show you how it changes for two-dimensional so that we don't have to write it twice, okay? So suppose f of x, y, z, three-dimensional, is continuous in a region D. Containing the curve C. And then we're going to encounter something that you haven't thought about in a little while. And C is described parametrically. By x of t, y of t, z of t, for some interval around t, so a less than or equal to t less than or equal to b, where x of t, y of t, z of t have continuous first derivatives. Then, so those are all of our hypotheses, all of our disclaimers at the beginning this time. The integral over C of f of x, y, z, ds, right, with respect to arc length, is the integral from a to b. Those are limits of integration on what variable? No? T. Do you see that one up there? T goes from a to b. That's where this is coming from. We're turning our function into a function of one variable. The variable is t, the parameter. So x of t, y of t, z of t. And the z of t gets multiplied by let me get my parentheses in there right, hang on. By a portion that's coming from the arc length. So this is x prime of t squared plus y prime of t squared plus z prime of t squared, all underneath the square root, times dt. I think I need one more parenthesis before there to close out the f of x work.
Oh, that's all I need.
It's just multiplied by the z of t. It's not multiplied by all of those components, just by z of t. All right, so this is the three-dimensional version. Let's just go back through, and I'm going to make a few notes on here about what changes in the two-dimensional version. You can choose to write them down, or you can choose to just watch and follow along. They're in your book, actually, all written out, nice and neat. But this is a whole huge paragraph, and it took me several lines to write it, and I don't want you to write twice. So if you take a look at this, if we changed this so that it would be for a two-dimensional version, obviously here you get f of x, y. right? Okay. We don't have x, y, x of t, y of t, z of t. We just have x of t, y of t. T still goes from A to B. That part's the same. And obviously we don't have a z of t here to discuss this with either. All right? And then our function down here, and I will rewrite this just so you have it written down, is the integral of f of xy ds. It's still the integral from A to B. And I still have my function that's x of t, y of t, but I don't have a z of t. So I actually have the y of t that gets multiplied by the square root. So the square root is x prime of t squared and only y prime of t squared because it's the only other one. And then at the end I have dt. Oh, and I left out that parenthesis again. So this is for the two-dimensional version, and this one's for the three-dimensional version. Awfully similar, right? They've all got the same types of conditional statements at the beginning. A little definitional thing we're going to come up with, or we're going to state right now just to make it a little bit easier for us later, is that we call the curve smooth. If it satisfies Theorem 2.1, the one we just wrote down, and x prime of t quantity squared plus, I think I've got too many brackets now. Look at that. That's what happens. X prime of t quantity squared, y prime of t quantity squared, plus z prime of t quantity squared does not equal 0 on the interval AB. Now, since those are all squared, what is that actually telling you in terms of this function? I mean, how would this fail? Let me say it that way. They were all positive, right? Like if you square things, you get positives or 0. So in order for this to actually equal 0, all of those derivatives, those partial derivatives, or not partial derivatives, but all those derivatives of each of those parts would have to be 0 to begin with, right? Which would mean they would actually all have to be original graphs of what? What would you have to do to get them all to be 0? I think somebody said it, but I'm not seeing. Close, not just lines, constants, right? Lines have slope, at least potentially they have something that's a non-zero slope. So in order for this to fail, we would have to start out with something that was just constants, right? A constant at x, a constant at y, a constant at z. So, and then the two-dimensional version of this, of course, looks the same, but it doesn't have the z component. Okay, so we're looking at something that's, at the very least, not a constant in all three directions. It is okay to have it a constant in one direction, and we're going to do at least one example I know where we have that going on. But all right, you ready to try one? Of course you are. I know you guys are. You're excited and you're ready to go. All right, so here's our first example. We're going to evaluate the line integral over C of our function f that we're given, again, with respect to arc length. And the first one we're going to do is going to be a two-dimensional function, f of xy equals 2xy. C, the curve we're going to do this over, is the line segment from the ordered pair 1, 2 to the ordered pair negative 1, 0. It may help you to draw a picture, it may not, but you could draw a picture of those two ordered pairs in terms of your xy plane, because we were doing this in 2 dimensions. So I'm starting at the point 1, 2, and I'm ending at the point negative 1, 0. So the line segment that I'm looking at is this one right here. Now, for some of you, that's enough right there to be able to motivate you how to create a parametric equation. And I can reason through it myself in that way too. That's fine. And so if that's you and that's how you think, that's great. So if you can just jump from here right to creating a parametric equation, more power to you. I want to show you a little bit different way of doing it too, though. I was trying to think of another option besides just motivating you visually to sort of reason your way through it, that you could do a little bit more concrete, with a little bit more written down details. All right? So it's often helpful. In fact, most of the time you'll see, if you're comparing the things of the examples of the book or so forth, the limits of integration on t going from 0 to 1. That's a pretty standard thing to do. There's at least one place in our examples today where I'm not going to do that, and you'll see why it doesn't make sense there. But most of the time, especially when you're doing a line segment, making t go from 0 to 1 is sort of the standard convention. Okay? What I'd like for you to do is to think of the fact that if t is, this is my t values, t is going from 0, in fact I don't want to write it that way, to 1, it's almost like I have an ordered pair relating, or a relationship anyway, a function relating t and how t is operating on the real number system. I'd like for us to write down what happens to x like this and y. What value does x start at? It starts at 1, and it goes to negative 1. And the directional sense right there is actually with what we're describing in this particular point right here. Yeah. What is y's mapping? 2 to 0. So what you could do, and what we are going to do, is we're creating equations that relate x to t and y to t, right? And this is a line. This is a linear relationship. We can actually look at these piece by piece, much like you looked at back in, an algebra course at finding an equation of a line here. So in this sense right here, we're actually looking at the ordered pairs t, x. T is my input, x is my output. Okay, so let's think about what you know. Tell me just real quick, I know you guys know this, some of you tutor in this kind of stuff all the time. What is the equation, point slope equation for a line in terms of x and y? What's it look like? Mm-hmm. Right. Right, that's the point slope form of a line. It's probably been some years, in fact, since some of you first learned how to do that, several years. Well, we're doing this same thing, but we're doing it instead of with x and y, we're doing it with x and t. And we're going to do it with y and t in a minute, too. So in terms of this sort of standard view of the equation, what we have, though, is that we have x as the output, so this will say x minus x1, and we have t as our input, so this will say t minus t1. And my slope is my slope of this situation with x and t, not the situation with x and y. So this ordered pair, you can think of these as an ordered pair as well, is the ordered pair 0, 1, from comparing this 0 and this one, right? This is my ordered pair 0, 1, and this is the ordered pair 1, negative 1. So if I'm looking at it from this perspective, what is the slope of those 2 points, the slope of the line between those 2 points? We'd do negative 1 minus 1 over 1 minus 0, right? So what does that give me? Negative 2. So up here in my equation, this is negative 2. And then I can take either of the the tx pairs that I want, and I can plug them in. So I like things with zeros because they mean I have to do less work. So I'm going to use this one. So t is 0. That's my t1 that's here. X is 1. So I have minus 1. So my parametric equation is actually x minus 1 equals negative 2t. Or x equals, you can write 1 minus 2t or negative 2t plus 1, of course. And that would be the parametric equation relating x and t. That's probably the most awkward one to write simply because we're putting x where we normally put y. The other one's a little bit cleaner for us to think about because we keep y in it as it originally was. So the one I'm going to do next is going to be y minus the y1. I have my slope and I have t minus t1. But I'm doing it comparing t and y over here. Let me highlight actually to give a different view of this. Oops. So these two are the ones I'm comparing. So if I think about these as an ordered pair, what's my ordered pair for this one? Uh-huh, 0, 2, and 1, 0. That's what happens when you don't erase. All right, so 0, 2, and 1, 0. And we can find this slope, same as we did before. I can do 0 minus 2 over 1 minus 0, or some variation of that, and I end up getting a slope of what? It's negative 2 again. All right, so my slope over here is negative 2. And I'd like to use the same t value I did before. So the ordered pair that well, either one of them actually works fine. I'll use this one just for fun this time. So this one's 1 and then 0. So the 0 is going to go in the y1. The 1 will go into the t1. And then we can solve this. So I've got y equals negative 2t plus 2, or 2 minus 2t if you prefer. And I kind of made that long and drawn out. You can do that much quicker. If you think about it visually, you can actually talk about, if you've let t go between 0 and 1, you can actually take a look at how y and t are changing. Because if t goes between 0 and 1, then the denominator for slope's always 1, right? Are you with me? So you can actually look back in here and you can say, well, how in the world is my t or my x value changing? Well, if you take a look at it, x started out here and it went here. Well, it's negative 2. So my slope has to be negative 2 because my x value is changed by 2 and in the negative direction. You can do the same thing with y. Y started out at 2 and now it's at 0. It's changed by 2. So my slope is negative 2 for that same reason. The trickier part is not the slope. It's making sure that you get the coordinates into the right places for the x1 and the t1, or the x1 or y1 and t1. So we have these two equations for x and t. These are my parametric equations, and that's what I need in order to do this line integral. Okay? So far I haven't done any calculus. Isn't that great? So let's actually do some calculus. So the next thing I'm supposed to do, or what I'm supposed to do, is let me go back over here to this equation. I need to take derivatives of these things, right? I need the derivative of x and I need the derivative of y. And that works out very nicely because these equations are equations of what? No one knows? What are these equations of? Lines. So what is the derivative of each of these? They're actually both negative 2. You betcha. So the square root part that we've been looking at, and I'll put it into the formula in a minute, but let me just work through it with you. In some cases it's helpful to see that separately. It's going to be negative 2 squared plus negative 2 squared, which gives me the square root of what? 8, which simplifies how? To square root 2. So that's going to be a part of my line integral that I'm taking the integration of. All right, so my integral over c of the 2xy, which I'll come back to in just a minute, is going to be the integral from 0 to 1, because those are my limits on y. And at the very end here, I'm going to have a 2 square root of 2 dt. Everybody good with that? Now what's supposed to go in between is the 2xy. It's the function. Yeah? Okay, so, and maybe I put my parenthesis in the wrong place now that I'm thinking about the way that I defined that earlier. I may have a parenthesis in the wrong place, Caleb, because you asked me a question and I think I told you wrong. We'll write it out and we'll figure it out. We have this function 2, x, y, so there's a 2. But what is x in terms of t? 1 minus 2t. So we have to substitute that in. And what is y in terms of t? 2 minus 2t. So I did tell you wrong before, now that I'm writing it out. This parenthesis over here was just in the wrong place. I knew I had one missing and I thought that I knew where it was. I was wrong. It should be over here. I'm sorry, guys. Just like that, it's cleaned up and it looks great. All right, so the first thing I need to do is I need to distribute everything out, simplify in order to actually take the integral. I like taking integrals of 0 to 1, though. Those are very nice values. So let's multiply this out and see what we get. All right, so the 2 here and the 2 square root of 2 here is 4 square root of 2. I'll do that in a minute. Let's just FOIL out the part that's inside the parentheses. What does that give me? I'll start at 2, and then what? 2t? I think it's more. Oh, sorry, I was combining mine and you weren't yet. Yes, so I have 4t here and I have 2t here. So I actually have 6, don't I? Okay, negative 6t. And then somebody was telling me the end part already, 4t squared, right, Tally? That's the part you were saying. You're right. If you'd like, we can do the 4 square root of 2 later. We don't even have to deal with it, right? And we can integrate. That's actually a better option even yet. So we've got 2t minus 3t squared plus 4/3 t cubed. Integration with the number 1 in a polynomial is fantastic because it's just the coefficients. Integration at 0 is even better because it's 0. So this ends up giving me 4 square root of 2 times 2 minus 3 plus 4/3. And, I mean, technically it's then minus 0 because of the other part, so that we didn't just sort of gloss over that. But if we combine these and simplify these, I'll spare you the details, we end up getting 4 square root 2 over 3. Is that all right? So far, so good. Okay. I have one of those theorems more we're going to write. Theorem 2.2. Theorem 2.2 is one of those things that if you didn't have it, you probably would assume it was going to be true anyway. And so that's a friendly way to have a theorem, is that it's one of those things we would expect to happen. Suppose that f of x, y, z is a continuous function in some region D containing the oriented curve C. Then, if C is piecewise smooth, with C equal to C1 union C2 union Cn. Okay, continue on that process. Where C1 up to Cn are all piecewise smooth, and the terminal point of C sub I is the same as the initial point of C sub I plus 1. For I equal 1 up to n, then we have two statements that follow. The first one, the integral over the curve backwards, in the opposite direction, is the same as our regular integral going forward. But more importantly, and that's where the C1, C2 businesses that we have above, if we took the integral over C of f of x, y, z ds, we could break it apart into the integral of C1 of f of x, y, z ds, plus, and we can continue doing each of these integrals up to the integral of Cn of f of x, y, z ds. So we're about to hit an example of one of these concretely, but the idea of this initial point, terminal point, is that if you have a whole bunch of piecewise smooth curves, this all works out just fine as long as their endpoints match up. In other words, we need it to be continuous, right? This curve has to be continuous, but each of the pieces individually can be some other curve described in a different way. Okay? So far, so good? Let's do an example. Oh, sorry, I have one more theorem to present, and then we'll do an example. It's a short one, though. That wasn't what I wanted. Okay, theorem 2.3 says the following. For any piecewise smooth curve, C, in 2 dimensions or 3 dimensions, the integral of the curve over the value 1 ds gives us the arc length of the curve C. Which makes sense, right? We're taking the integral with respect to s, so that's what we would be getting. All right, so let's do example 2. You'll notice that the directions are going to change slightly, and it's not in this example, though. Sorry, it's the next example. This example, same directions. I'll rewrite them since we've had a few slides in between. We're going to evaluate the integral over C of f ds. And the second example that we're going to do is f of xy equals 2y, where C is the portion of y equal x squared from 0, 0 to 2, 4, followed by the line segment extending to 3, 0. And I think a picture of that might be in order to give us some perspective. So you all know what y equal x squared looks like, something like this. And we'll say this is the value 2 down here. We're at 4 right there. And here's 2. So this is the portion of the y equal x squared that we're supposed to be going from. And then once we stop there, it will be extending from this point down to the value of 3, 0. Are you with me on the picture? Okay. So this is an example of one of those pieces where it's piecewise smooth. Each of those pieces will work, but we have to do it in 2 pieces. Okay. So the first thing we're going to do is we're going to label these, just so we have it, as C1 and C2. And we'll just do them one at a time. And then when we're all said and done, what do you think we're going to do with our 2 line integrals? We're going to add them together. So we're doing 2 separate line integrals, and then we're going to add them. A line integral on C1 and then a line integral on C2. So the first thing we're going to be doing is we're going to be doing a line integral on C1 of our function. And then we'll do a line integral on C2. Oops, that's not written right. Line integral on C2 of our function. All right, so we're going to do this one first. Here, I mentioned earlier that it's typically the case that we're just going to let t go from 0 to 1. And that is true. We're typically going to do that. And we still could do that on this particular problem, but on this particular problem, it's actually kind of nicer to let it do something different. So my t values are supposed to be going, or my points are supposed to be going from 0, 0 up to 2, 4, right? And they have this relationship of y equal x squared. And that's fine. But it's actually quite easy to do this parametrically if we simply let x equal to t. So we're going to let x equal to t. And if we did that, what would y equal? T squared. What would be my limits of yeah, they are my limits of integration as well. But what would be my limits on the parametric t, on the parameter t? Where would t start? 0. And where would it end? 2. So it's simply very natural to let it go from 0 to 2 there. Does it have to? No, it wouldn't have to. We could create it to do something different, but why would we want to bother with it when this works so naturally? Make sense? Okay, so we're going to find then x prime of t and y prime of t. So what's the derivative for x? No, but good try. 1, yes. What's the limit for y? Not the limit, the derivative for y. 2t. So the square root that I was dealing with earlier, I'm going to have the square root of 1 squared plus 2t squared. So what's the square root going to be? Right, 1 plus 4t squared. And just so that you realize what you're getting, this is ds dt is what you're finding. If you're trying to think through what piece you're actually finding, you're finding ds dt. All right, so we're going to do that integral now. So we have the integral over c1 of, what was our original function? 2y ds. So our limits of integration on this one are 0 to 2. We've got a 2. What is the value for y? T squared, right? T squared. And then I have to use the square root value that we had, which was 1 plus 4t squared dt. All right, does that look okay? Now what? Huh? We are going to do C2 in a minute. Let's finish this line integral first. What do you think? It could be an integration by parts. It would be a messy integration by parts, though, because no matter which one you let u or dv be, we're going to get something more complicated when we do an antiderivative, right? U substitution might stand a chance, but we're going to potentially run into problems with that as well. Do you see why? All right, so at this point on this one, we're going to let our calculator just approximate it for us on this one. The ones that I do on the test aren't going to have that sort of flavor to it, but this one does, and I want you to be aware of it. Yes, Nidra? What's that? Yeah, absolutely. Sure. This approximation. If we use our calculator to approximate this, this gives us 16.9424. And do you guys remember how to do that in your calculator? It's the Math 9 feature. You put this in your calculator. You use, of course, x instead of t. And then you do, well, my version of it actually pulls up this thing called nderiv. I would put this equation in y1. And then you do x, and then your lower limit is 2, and your 0, and your upper limit is 2. For those of you who have math type using in your calculator, it actually shows it to you in more of the traditional view anyway. All right, so this is C1's line integral. Nathan, you mentioned we would need to do C2 as well, and you are correct. But in order to do C2, what am I going to have to do? Yeah, I need equations, and this is an equation with parametric equation with a line, correct? Yeah? All right, so I'm actually starting out at the point 2, 4, wasn't it? 2, 4, and I'm going to be turning this into the point 3, 0. And again, it's very natural to let t go between 0 and 1. So in terms of the x values for slope, so let's find the slope for x, the x values. The slope in terms of x, what is x doing? How is it changing? It's increasing by 1, right? So that's my slope for this one. How is my slope for y changing? It's -4. It's decreasing by 4. It's starting at 4 and going to 0. So those are the individual slopes. So we're going to do x minus an x value equals the slope, and then t minus a t value. And then we'll do the same thing for y in just a second. So x minus an x value. Let's just do the initial x value. The initial t value is 0. What's my initial x value? What is it? It's 2, right? My initial x value is 2. Okay. So this ends up giving me x equals t plus 2. And then over here, my initial y value is actually 4. The initial one, the very first one where I start, is 4 for this segment, for C2. And then this is -4 times, again, my t value is 0 where it starts, so I've got t minus 0. So this ends up being y equals -4 t plus 4, or 4 minus 4t. So these are my parametric equations. Let's do the derivatives of them, because we've got a little space here to do that. What's the derivative of x prime of t? 1. And y prime of t? -4. It's just the slopes that I found earlier, right? All right, so we'll do this one here in just a second. We'll move it down. Let's do the square root value. So I've got the square root of 1 squared plus, it's technically -4 squared. What does that give me? Square root of 17, exactly. All right, so my integration limits are going from 0 to 1. I've got 2, and then I have times y. Y is 4 minus 4t. And then this is multiplied by the square root of 17 dt. And if you'd like, you can put the square root of 17 out there in front. This is the square root of 17, and then 4t minus 2t squared. Evaluate it at 1 down to 0. Of course, that means just pretty much evaluating at the value 1. So that gives me square root of 17 times 2. Does that look right? 4 minus 2. I'm missing something. What am I missing?
From up there, from the very first.
That's what I lost. I'm like, I'm off by a factor of something. Let me put the 2 back here then. There we go. Thank you. 4 square root of 17. There we are. And then our entire line integral will be to add this piece together with this piece, which was, the first one was an approximation, so turning all of it into a decimal at that point makes a lot of sense. So if I were to add those two together, the entire integral for f ds is what? Approximation, 4 decimals.
33.4348.
33.4348. Any questions on that one? All right. All right, we're going to do definition 2.2. And this is another definition of a line integral, but it's not the line integral with respect to the arc length any longer, okay? So the line integral with respect to x and we could do it with respect to y or with respect to z, and we'd have the same kind of description. Along the 3D space is defined by integral over c of f of x, y, z dx equals the limit as the partition goes to 0 of f of xi, yi, zi, delta xi. And we've got the same conditions we had just a moment ago, provided the limit exists. And is the same for all choices of evaluation points. And if we wanted to do the line integral with respect to y or z, very little changes in this description, of course. This would be y, this would be dy, this would be, no, not there, there would be dy sub I. We could do the same thing for z, right? That's all it's going to change. Practically speaking, what does that mean for us? Well, it means that when we do this with the theorem, we've got 3 options as well, since we have x, y, and z. So theorem 2.4. It's an evaluation theorem. Again, going to feel a little bit like that other evaluation theorem that we had before. It says the following. Suppose that f of x, y, z is continuous in a region D containing the curve C. C is defined parametrically by x equals x of t, or, let me just say this way, by x of t, y of t, z of t. Where a is less than or equal to t is less than or equal to b. And each has continuous first derivatives. Right. Then, the integral over c of f of x, y, z dx, because that's the first one we're going to do, as described, is the integral from a to b of f of x of t, y of t, z of t. So it's that same function that we had, but in terms of the parameter t, times x prime of t dt. What do you suppose will change for my second formula if I do the integral with respect to y? I'm going to have y prime at the end. That is the only difference. And for z, you'll have z prime at the end. And we will stop right here and we'll pick up next time where we left off.